Hello and welcome to this lecture on fundamentals of electric drives. In this lecture, we will be discussing about current source inverter fed induction motor drives. Previously, we have discussed the voltage source inverter fed induction motor drives. For very high power application, current sources are preferred because they are very rugged compared to the voltage sources. Now, we will be discussing about current source inverter fed induction motor drives in today's lecture. Current source inverter we abbreviated as CSI. Now, these are used for high power application as we have already discussed. Primarily in megawatt ranges. Now, if we draw the circuit diagram of a typical current source, which is realized by means of thyristors, the current source will appear as follows. So, we have the SCRs and the diodes. These are the SCRs and these are the diodes. We have two set of diodes here. We have another diode and another SCR. And we have a DC link. The DC link has a large inductance. We have the capacitors between the SCRs and the diodes. They are called the commutating capacitors. Similarly, here also. And then we have the induction motor, which is the load. The input side, we have a converter bridge, which I am just showing in terms of a block diagram. It is a converter bridge. It is a 3-phase full controlled converter. The input is 3-phase AC. This is a 3-phase full controlled converter bridge, and this is our current source inverter. Now, these SCRs are named as T1, T2, T3, T4, T5 and T6. The diodes are similarly D1, D2, D3, D4, D5 and D6. The capacitors are C, they are all same value. Each capacitor is having the same value, that is C. Now, we will not be discussing the detailed operation of this CSI, which is usually done in a first course in power electronics. The capacitors are used for force commutation. The SCRs are triggered in the sequence T1 to T6, and then the capacitors are charged, and the capacitors are used to turn off one SCR when the next SCR is triggered. So, the sequence of the triggering is as follows. So, the sequence of triggering of the SCRs are as follows. Sequence of triggering of the SCRs are T1, T2, T3, T4, T5 and T6. And at any given time, if we neglect the commutation overlap, at any given time only two SCRs will be conducting. So, the SCRs will be conducting in pair T1 T2, T2 T3, T3 T4, T4 T5, T6 T1 and so on. So, the SCR conduction is as follows, it will be something like T1 T2. So, if T1 and T2 are conducting, we have this is phase A, this is phase B and this is phase C. So, these are the phase currents IA, IB and IC. So, when T1 and T2 are conducting, the current will flow like this and will return back through phase C. And after that we have T2, T3, T3, T4, T4, T5, T5, T6, T6, T1 and the sequence repeats. Again we have T1 and T2. So, we see that at any given time two SCRs are conducting and one SCR conducts for 120 degree. So, this interval of conduction is 60 degree and we have 6 changes in one complete cycle. So, any SCR is conducting for 2 segments which is 120 degree. So, here we have T1 and T2. So, and then we have T3 and T3 again. So, this interval is 60 degree and an SCR will be conducting for 120 degree. So, each interval is 60 degree here. So, as a result the output current, if we are supposed to plot the current here in this case, let us say we will be plotting IA against time or omega t here angle. So, this IA will be a quasi rectangular waveform of this sort. So, this duration is 120 degrees, this duration is also 120 degrees. So, the inverter current here, the input current is let us say II and the output is IA. So, this is plus II and the negative side in this case is minus II. So, if we see the fundamental component of this is phase current IA. Similarly, phase B and phase C will be shifted from phase A by 120 degree and so on. So, this is phase A current. So, RMS value or the fundamental component IS is the RMS value of the fundamental component of output current. That is equal to 4 II by pi, 4 II by pi, this is the into cos of 30 degree. This is the peak value. So, since we are calculating the RMS value, we have to divide by root 2. So, this is 2 into root 2 II by pi, and cos 30 is root 3 by 2. So, we have finally root 6 II by pi. So, it means if we know the inverter input DC current, we can calculate what should be the RMS value of the stator current or the output current of the inverter. This current is flowing in the induction motor, which is responsible for the torque production. Now, in this case, since we have an inverter, we can what we can vary here, we can vary the output current and we can vary the output fundamental frequency. So, the fundamental frequency, if we see the fundamental current of this would be the fundamental component of this, which we can find out by Fourier series method. So, this is the fundamental component of the current and the RMS value of that. So, we can change the RMS value of the current, we can also change the frequency. By changing the fastness of switching, we can change the frequency. So, we have a variable current and variable frequency source. So, we can change the stator current, we can also change the stator frequency. So, if we apply this principle to the induction motor, we can draw the equivalent circuit of the induction motor. We have the stator resistance and reactance, then rotor reactance and the rotor resistance here. So, this is our equivalent circuit of induction motor, and we place our magnetizing branch here. So, we do not approximate, we draw somewhat exact equivalent circuit. The losses are included in the output. So, this is the stator resistance, the stator leakage reactance, the rotor leakage reactance, the rotor resistance referred from the primary side and the magnetizing reactance, and here we do not have any voltage source, but we have a current source. So, the current source is having a value IS RMS value is IS here, IS ampere the RMS value. So, the rotor current here is IR and the current in the magnetizing branch is IM. Now, this is our equivalent circuit, we have a current source here. So, we can find out what is IR prime. So, IR prime in this case the magnitude is the input current is the same current IS which is flowing into this path. So, this is IS amplitude into XM divided by RR prime by S whole square plus XM plus XR prime whole square, and this is under root. So, this is the value of the rotor current. Now, we can find out the torque equation. The torque is given as 3 by omega ms into IR square into RR prime by S. So, this is the expression for the torque of an induction motor. So, we substitute the value of IR prime here. So, that is equal to 3 divided by omega ms into IS square XM square divided by RR prime by S whole square plus XM plus XR prime whole square. So, this is in the denominator. So, into R r prime by S. Now, this is the torque versus slip. So, torque is a function of slip. Now, we can find out what is the slip for the maximum torque. Since this is the expression which gives the torque as a function of slip, we can find out what is the slip for maximum torque. So, slip for the maximum torque can be found out, and we can very easily say that S max T, since we are having in the denominator x m plus x r prime, x max T is the slip for maximum torque, that is equal to R r prime divided by x m plus x r prime. So, this is these two quantities should be equal. So, we have in the denominator the slip resistance and also the reactance. The reactance is x m plus x r prime and the slip value is R r prime by S. So, when they are equal, the slip will be, the torque will be maximum. So, if we analyze this value of S max T, so what we get here is this x max T is R r prime by x m plus x r prime. Now, this is a very small quantity, this is much smaller than 1, because we have the magnetizing reactance which is a large reactance. The leakage reactance is a small value, but the magnetizing reactance is a large reactance. So, the slip may be of the order of 0.001 or 0.002. Now, if we plot the torque speed characteristic of a CSI fed machine, so this is omega m and the torque, this will be the nature of the torque speed characteristic. Very low value of slip for which the peak torque occurs, and then we have a low starting torque. And if we go on varying this current, we get family of curves like this. So, this is for IS1 current, this is for IS2 and this is for IS3, and this is of course is the synchronous speed which is omega ms, the origin, and we have the torque speed characteristic, and this slip for which we get the rated torque is very, very small. So, this is the operating slip. Let us say we operate corresponding to IS1, this value of slip, this is the speed here. So, slip will be of the order of something like 0.001, which is a very small value. This is the slip for the rated torque, this is the slip for rated torque. Now, if you see the equivalent circuit, when slip is very, very small, the slip resistance is very large. So, this quantity, the resistance becomes large. So, since the resistance becomes large, current predominantly flows through the magnetizing reactance. So, this leads to saturation of induction machine. So, at this point, although we operate at maximum the rated torque here, the machine is heavily under saturation. So, it is not advisable to operate it here, and if we plot a corresponding VSI fed machine, this is the corresponding VSI fed machine, VSI fed induction motor, the rated slip is much higher than that. So, this is the operation which is corresponding to the rated value of flux. So, we understand here that if we want to operate a rated value of flux for a CSI, the characteristic lies in the so called unstable region of the CSI, because CSI characteristic is this one. So, the operating region here is so called unstable region of the CSI. So, it means if we want to operate the CSI with constant air gap flux, we have to have a closed loop to stabilize the unstable CSI. So, CSI is never operated under open loop condition. A CSI fed induction motor drive is always operated with a closed loop feedback. CSI fed induction motor requires closed loop feedback, closed loop control for constant air gap flux operation, air gap flux operation. So, we have to keep in mind that we are operating at constant air gap flux. So, if you want to have constant air gap flux, we have to operate somewhere here, and this requires a closed loop feedback because the CSI is so called operating in the unstable region. Now, let us see the operation of CSI with constant air gap flux. We can draw the equivalent circuit once again. This is our equivalent circuit that we drew earlier. We have the stator and the rotor, and then we have the air gap or the magnetizing branch here, Xm, Xr prime, Rr prime by S, Xs and Rs, and we feed this from a CSI. The CSI is represented by a current source. Now, this is our rotor current IR, and the stator current is the magnetizing current is Im. The stator current is of course Is here. Now, if we want to find out what is Im in this case is the magnetizing current, which we want to keep constant. So, the magnetizing current should be kept constant for constant air gap flux operation. Now, what is Im? Im can be obtained as Is is the current which is flowing into this. This is the source current, the stator current, that is Is, and we are interested to find out what is Im. Im is Is into Rr by S whole square plus Xr prime square under root divided by under root Rr prime by S whole square plus Xm plus Xr prime square. Now, we square both the sides here. So, Im square is equal to Is square into Rr prime by S whole square plus we separate the frequency here, this is 4 pi square f square into Lr prime square divided by Rs by S whole square plus 4 pi f square into Lm plus Lr prime whole square. We divide by f square, so that is equal to Is square R by Sf whole square plus 4 pi square Lr square divided by Rr by Sf square plus 4 pi square Lm plus Lr prime square. Now, in this case S into F is known as the slip frequency. So, what we do here, we control the slip frequency of a CSI fed induction motor. Now, slip frequency can be changed from 0 to certain value. Now, if slip frequency is very small, what happens? So, we are controlling the slip frequency here, and let us see what is the relationship as we change the slip frequency. Now, this relates the magnetizing current with the stator current with the slip frequency here. So, let us say if SF is small or SF is very small, if SF is very small, these parts can be neglected. These parts are small with respect to this is dominant here. So, this is also can be negligible. So, what we get here is the following, that I m square is equal to I s square into R r prime by S f whole square divided by R r prime by S f whole square, or that is equal to I s square, or which implies I m equal to I s. So, if S f is very small, the stator current, the RMS value of the current is same as the magnetizing current. Okay. Now, let us see that if SF is moderately small, if SF is moderately small, if SF is moderately small, what happens here? If it is moderately small, we can neglect this. What we do that here, we neglect this quantity. This quantity can be neglected, this is 0, and if SF is moderately small, but still we have some value of SF, it is not very small. So, this quantity still dominates. So, this part can be neglected. So, if we neglect the denominator 4 pi square L r square, and in the numerator we can neglect R r prime by S f approximately, what we get is the following. We get in this case I m square equal to I s square into 4 pi square, that part is neglected. So, R r prime by S f whole square divided by 4 pi square into L m is a large inductance. So, that will dominate L r square, or if we simplify this, we will get here that I s is equal to I m into 2 pi L m plus L r prime divided by R r into S f. So, what we get here is that the stator current varies linearly with the slip frequency. So, this is the relationship that we have, that this is the slip frequency, I m is constant. So, if we draw the relationship between the slip frequency and the stator current, RMS value of the stator current, we find that if S f is very small, I s is constant, the same as, and this is for I m is kept constant. So, this is constant here, and then after that this is proportional to the slip frequency. As the slip frequency increases, the stator current also increases. So, in the negative side also we can plot it in a similar fashion. So, this will just a mirror image of this quantity. So, this is how the current varies with slip frequency. So, it means if we want to change the slip frequency, we have to change the stator current accordingly. So, with this in mind, we can now think of a control of a CSI-fied induction motor, where we change the slip frequency and the stator current is changed in accordance with the slip frequency to maintain the magnetizing current constant, or in other words maintain the air gap flux constant. So, we stop here for today's lecture. We will continue with this discussion in the next lecture.